Hi. So what we've got here is a worked example for a proof by induction. So we'll look prove by induction that for all positive integers n, the sum from 1 to n of log 2r minus 1 is equal to this log here, 2n factorial divided by 2 to the power of n times n factorial. Now it looks a bit of a beast, and to be perfectly honest, it really is one of the harder problems of this type. Um, so the I mean the thing to observe here, of course, is we've got a log of a sort of a product of and then quotient of things here, and of course the log of a product is equal to the sum of the logs. So that we're going to use that identity in order to help solve this. Right, so let's have a go. All right, so establish the base case is what we do first. And if we look at the case where n is equal to 1, then the left-hand side is just one term, basically works out to be equal to the log of 1. And the right-hand side, again, if we substitute in 1 for n in there, we're just going to work that through and again get log 1. So it is true for n equals 1. Right, so at the substantive stage, we are just assuming this is true for n. Right, so now we're going to try and prove it's true for n plus 1 on the basis of that assumption. So this sort of broad approach essentially is to look at this, add in the n plus 1th term, which we can derive from by looking at what that extra term would be if we were going to n plus 1. Add those together and then rearrange. And what we should end up with is something that looks very much like this, except with n plus 1 instead of n. Okay, and that establishes the fact that it's true, therefore, for n plus 1. So let's have a look at that. So by default, we're going to define this as convenient notation to being equal to this right-hand side. And that is, if we apply our log rules, is going to be the log of 2n, and then every integer down from that, log of 2n minus 1, and so on, 2n minus 2, all the way down to, well, all the way down to log of n plus 1, because obviously we've got cancellation here. So the last n terms from n factorial, n minus 1 factorial, and so on down to 1 factorial will cancel out from this numerator. So it just leaves us with those terms. But then, of course, we've got to take into account this 2 to the power of n on the denominator, so we're just going to subtract the log of that. And in fact, I've written that as n log 2. Okay, so that's the contribution of this bit in this expression. Right, so what is the extra term then, which I've written as the difference between the two here. So if we sum to n minus 1, then the difference in that is just the n plus 1th term, f of n plus 1 minus f of n. And that's just, we're sort of just going to evaluate this with n plus 1 in. And that's going to be equal to that. Okay, 2n plus 2 minus 1. All right. So now then, so we've got an expression for um, for fn plus 1. If we add this is the nth term here, and this, then what we're going to get is this. This term we'll put up front here, and then this lot basically is just what we've got here on this line. Right, okay, so that's what we've got. Let's have a look. Log of f of n plus 1 is log of 2n plus 1 plus log of 2n plus log of 2n minus 1, blah, 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 all the way down to log of n plus 1. Okay, and then we've got the subtracting um, this term here. Right, now this is the trick really, and this is kind of I thought what makes this rather difficult is we this term doesn't really go far enough. If we want to actually show this here, what we want is in that case we want 2 into n plus 1, which is 2n plus 2. So we need a log 2n plus 2 term. Right, well, we've just put it in, but the trick really is that, I've subtracted it as well. So this is a bit of manipulation that is actually this sort of thing is really kind of quite hard to see. But anyway, so we put that in there. So we've got now the log of 2n plus 2 and all the integers down, 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 down to these two. And then that's extra term at the end, and then the sort of the subtraction of that. Right, so I've written it like that. So I've highlighted the red because that's this sort of this kind of rogue term that we've had to introduce. But what the next line basically is exactly the same. I've just changed the coloring just to sort of help with the explanation. So we've got this lot here. All right, so just the same as above, and then I've put this in green because we're going to handle this slightly differently. Right, so what we got with this, so again, going back to the log rules. Okay, so I'm going to write this as the log of, well, this is 2 into n plus 1 here, isn't it? And we've got all the following terms. So it is a sort of fact, it's a factorial, isn't it, of that? I mean, maybe there's a bracket missing there, but um, um, all the way down to, well, if we're going down to n plus 2, we need to cancel that ones below that, which is log of n plus 1, log of n, log of n minus 1, and so on down to the log of 1. We need to cancel those, and we're going to do that by subtracting this log here. Okay. So in actual fact, this is a whole set of logs. If we were uh, to expand out the factorial, and so is this, and that difference basically is what we've got there. Okay. Right. Well, now we're still left over with this green bit here. Um, So we've got to do something with that. So, okay, so now looking at these two together, I'm going to write this as a single log. So using the sort of the second log rule as I see it, the one that deals with division and subtraction. So we've got the log of this minus the log of that there. Okay. And then with this, we've got the log of n plus 1 there minus n log of 2, I've kind of converted that back there to 2 to the power of n. I don't know whether I needed to convert it in the first place, but that's 2 to the power of n. And also on the denominator, I've got 2n plus 2. Now, what we've got now that we've introduced this term here, what we've got is got cancellation going on there. So this that cancels with that, leaving a 2 there. And of course, then we can express that as 2 to the power of n in a moment. Right, so we've got that term. That's simplified with the n plus 1 cancellation going on. And then if we merge these two, again using the log rule, sort of we've got the product of this and this. So when we roll these two terms together, we've got the numerator there, that's that, and we've got 2 to the power of n plus 1 there, and then we've got our n plus 1 factorial from there. Okay. Right, okay, so having written it like this, I think we can see that this actually, therefore, is exactly the same as this, but for n plus 1. Okay, we've got n plus 1s for every occurrence of n in this statement here. So that is what f of n plus 1 is. And so therefore, the conclusion is so that um, uh, f of n plus 1 equals this expression. And so therefore, this identity is true for any n. Being true for n implies it's true for n plus 1. And since it's true for n equals 1, then it is true for all n. Right, okay, yeah, not an easy one at all. Now this little trick here, I mean, in part, you could say it's part of the 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 process that I've used, which is to add into the nth term, add the extra one, and then reorganize it. I mean, it's possible that if we'd actually done it the other way and actually written the n plus 1th term of that, and then subtracted the n plus 1th term and reorganized that, then it might have been, might not have required this sort of inventive step here. I don't know. I haven't worked it through that way. But either way, yeah, a bit of a tricky thing, really. But uh, hopefully that has been of interest and of use. So, uh, thanks for watching.